Here we have another complicated static equilibrium problem. Nothing is twisting, nothing is accelerating, so our equations for static equilibrium will hold. Net force in the x direction equals 0. Net force in the y direction equals 0. And the net twists, the net torque, is equal to 0. In order to understand and use these equations, we certainly need to make an accounting of all of the forces on the object of. So find the tension in this cable. Well, what's in static equilibrium? Let's identify the object in question. The object in question is this beam. It's the object on which there is tension. So if we want to find this tension, then we need to consider this object to which this tension is, on which this tension is affecting, and this object is the beam. But let's limit it to the beam and think about now all of the forces on the beam. Forces come from weight, and the beam has a weight. It says it has a center of mass, and it's located basically because it's a symmetrical beam. It's located in its geometric center, and it's given. I think everyone has, so this is the weight of the beam. I'm just going to put it as weight. There's a tension downwards caused by the weight of the barrel. So this tension, because this barrel is not accelerating and there's nothing below it, this tension is going to be equal to the weight of this barrel. This barrel is pulling down on this wire, pulling down on this beam. On the other hand, this wire is holding this whole beam up. So there must be a tension in this wire as well. So I'm going to call this tension up. There's a tension up here. So there's 2 points of contact here. There's opportunities for pulls. There's a point of contact here at the pivot point, and there is forces here. I don't know what they are, but there's a possibility for a horizontal force, and there's a possibility for a vertical force. Now, I actually don't really know the direction. I'm just speculating, actually. I'm speculating down and up, but hopefully that should come out in the wash. So these are 2 components of some singular force that is on this pivot point. And the reason it's not just the normal force is it's coupled on there. So the wall can actually put a vertical force without worrying ourselves about friction. Basically, a couple, when you're bolted on, is like super friction. It's a force that gives the wall a possibility of applying a force parallel to its surface. There's always this is the normal force here, this pushing out, but a force that is not the normal force and is just like a super friction force when you bolt it. It's parallel, up and down vertically. Anyway, both of these together, I'm not sure what that force will end up being. We may or may not even have to find it, because we're, in part A, asked to find the tension in this cable. I assume they mean this cable here, tension upwards. Well, let's see where this shows up. What equation here does this tension even show up that'll even give me a hope to solve for it? Let's think about in the x direction. Let's think about the net force in the x direction, which we know is 0 because it's not accelerating, and nothing is accelerating in the x direction. Well, tension is vertical, weight is vertical, so I must have an f of x And if I lay down a little coordinate system here just to remind myself what's up, down, what's plus, what's minus, f of x, actually I don't even know what direction that is, but I know for sure that that this tension, as it's pulling up this wire, partially pulls up on the beam and partially pulls the beam towards the wall. So this, I certainly know this tension is pulling this beam inwards. So I'm going to put a little negative Tx there. That is going to have to be balanced. So I know that this force Fx is out because it has to balance this Tx, because together they must equal 0. So they have the same magnitudes in opposite directions, and that makes for quite a simple